Exploit blockchain.
Hello everybody, I'm Dima Kovalenko. I'm an Android and iOS reverse engineer. And today we will talk about some very specific technical things. I will try to keep these things as simple as possible, but sometimes we will dive into technical details. Okay, let's start with a very simple things. First point in the agenda is Cyanide Pointers. Consider a typical memory corruption vulnerability. The code flow is very simple. Application stores a pointer into virtual memory. Then something happens. Usually a hacker feeds an application with specially crafted data and triggers a mistakes made by developers. Usually it's overflow, different kind of overflows. For example, a developer does not control array ranges properly. And under some conditions, an application can write something out of the array. The pointer actually is stored in the same virtual memory as any other application data, alongside with other application data. And if under some condition an attacker, a hacker, we can rewrite the pointer, and then the pointer is used by an indirect branch instruction to jump somewhere, we can point code flow to a rope chain. Rope chain is an carefully picked pieces of programming codes in virtual memory, chained together with a branch instructions with jumps. And it's crafted to make application things which it's not designed to make. Actually, this is a typical code flow. And there are a lot of possible mitigation. One of the possible mitigation is to sign a pointer, to use a cryptography to sign a pointer. Actually, we use a cryptography to sign, for example, PDF documents to make sure they are not changed, right? That's normal practice. So why don't we sign pointers? Indeed, possible mitigation. Use some crypto to sign a pointer, then store the pointer to virtual memory. Then something happens, some code runs, doesn't matter. Then beneath the pointer, we load the pointer from the virtual memory, then use the same crypto to check the signature. And make sure the pointer is not changed, is not overwritten with some malicious exploit. If the pointer is not changed, we use it. If pointer was changed accidentally or maybe by some exploit, we throw an exception. The logic is actually very simple. And in theory, everything sounds great. But in practice, we have several problems. The first problem where to store the signature and how to bind the signature to the corresponding pointer. Actually, if we have a data and if we have a signature for this data, we should bind it together somehow. Actually, an average application uses millions pointers. So we need probably some dedicated memory for these signatures. And we need something like a, I don't know, dictionary in memory or something like this to bind together the pointers and the corresponding signatures and vice versa. Another problem is our crypto should be very, very fast, because storing pointer in the memory, loading pointer from the memory, and branching that pointer is a very often operation during any application execution, actually. So the crypto should be very, very fast. And the last, actually, main problem is backward compatibility. We should not break things. We should introduce new features in a smooth, light way. Do not break already existing systems. So these three problems was solved by ARM Corporation from my point of view, in a very brilliant way. Because what actually did they do? They introduced a new extension for ARM socket on chips called ARMv8.3. And just a brief introduction in the extension. It's an optional extension, so a vendor who makes ARM CPU can implement it, or maybe if he doesn't want, he may do not implement it. It's up to the vendor. It's for 64 mode only, for 64-bit code, and it adds, among other things, 46 new machine instructions to implement actually Cyanide pointers. And it is backward compatible with the standard ARM8 instruction set. Okay. Cyanide pointer in ARM is called Pointer Authentication Code, PAC. PAC is enabled if one of that four system register is equal to 1. I should say I am not really good in reading long English abbreviations. So I will skip it and just point to the slide, to the presentation, and say something like, look, there is the pointer, there is the register names, okay? Okay. The idea is to store pointer and pointer signature together. Well, in 64-bit systems, pointers are also 64-bit. But, in fact, the virtual memory range is limited by a system register. You see it in the first row. TCRLXTNSZ-1. This is actually range from the address. And we can use upper bits to store a pointer, pointer identification code. ARM proposes to calculate pointer authentication code, actually the signature, in this way. They propose to use pointer and modifier and key as input, and get pointer authentication code in upper bits, and the pointer itself in lower bits. This solves the first problem. The first problem, let me remember, will be where to store the signature. If we calculate the signature, where to store it? They store the signature together with pointer in the same memory cell or general register or whatever. The result is not a valid pointer, actually, here. And we need a special instruction to make it valid again. About the keys. Well, actually, the key is stored is exception level 1 register, so they are not accessible from user mode. It's a good thing to mitigate modern jailbreaks. You know, the modern jailbreaks usually starts in user mode. then try to evaluate privileges to higher exception level. Well, here we have a kind of mitigation, and we have 5 keys. It's API AB key, APD AB key, and APGA key. Different keys are used by different groups of instructions, actually. The key is expected to be temporary, actually, and the key management is up to software, up to operation system. We should not expect that hardware will do everything for us. We should take something to hardware side, and something should be managed by hardware. Hardware is responsible for generating keys, for managing keys, for clearing keys when we change exception level. And some instruction also need a modifier. Modifier is usually a general purpose register. The most often is stack pointer. In general, there are 2 big groups of the new instructions. Basic pointer authentication instructions. They only perform operation on pointers. They do not do jumps, branches, or whatever. They can calculate pointer authentication code. They can add it to the pointer. Then can strip it. Strip with checks and strip without checks, actually, if it's valid or not. And combined instructions that include pointer authentication. Each of these instructions combines a pointer authentication with another operation which uses the authentication pointer. For example, branch. Okay, we will skip this. And the solution of the last problem, backward compatibility, is very simple. They dedicated encodings for the new instruction from hint NOP operation, from hint NOP instruction range. And that's why for the older systems which do not implement the new instructions, all these instructions are just NOPs, no operation. This is why they have backward compatibility. And there is an example. The example is pretty simple. If you do not read ARM assembler, I will explain this in a simple way. It's nothing to be scared of. It's a typical instruction prologue, the beginning, and typical instruction epilogue, the end of instruction. In the prologue, there are several instructions, and the instruction saves a general pointer register called LR, link register. This register points to a return point from the actual procedure. And the epilogue read this pointer from memory to link register and use read instruction to return from the procedure. This is not protected code. And this is the same code protected with the new instructions. Before we store link register to the memory, we sign it with pointer authentication code and use stack pointer as a modifier. These guarantees 2 things. First, link register will not be alternated, will not be changed, will not be overwritten inside the procedure. And the second thing is stack pointer will save it in the virtual memory, will stay the same at the end of the procedure. In the function epilogue, we use another instruction to check and strip the pointer. If the pointer is valid, we will have the same pointer in link register. If pointer is not valid, this instruction, I see no pointers here. Anyway, this instruction will add some garbage bits to upper bits. And we will jump not to the exploit return-oriented programming chain, but into some probably unallocated memory, and it will throw bad access exception. Okay. It was a very, very short and brief introduction into pointer authentication codes itself. We do not consider cryptography yet. We will do it in 1 minute. Now I can recommend these links to dig a bit deeper into this point. First link is ARM architecture reference manual. It's a very, very exciting, very, very good storytelling guide. It's about 6,000 pages, and it's mostly tables. So it's very few text, mostly tables. Actually, I'd recommend also to look at Mark Rutland presentation and Qualcomm presentation, the presentation from Qualcomm team. Why Qualcomm, I will tell in a minute. Okay, the next point is Quarma. Telling the truth, I don't know how to spell it correctly. I was trying to find some video on YouTube to learn the correct spelling, but unfortunately I didn't find it. So we will call it Quarma. Quarma is a cryptography algorithm developed by Qualcomm, especially for pointer authentication code. What's the special about Quarma? First of all, it can give us a various output from 3 bits to 23 bits if memory tagging is used, and from 11 bits to 31 bits when memory tagging is not used. Actually, Qualcomm considered existing algorithms like zip hash, for example, or Prince, but all this algorithm was not okay. For example, zip hash was relatively slow, and it can make impact on the code flow and speed of system of chips. And Prince has a fixed site input-output, and cutting the output according to the needs was not enough secure from cryptography point of view. Quarma was designed by Qualcomm to be fast and produce short signature if needed. And Quarma was carefully tested, including cryptanalysis tests. So they developed an algo, and they tried to attack it as usually cryptanalytics do. It's hard to say if it's really safe, because actually the latest news shows that it's maybe not really safe. Anyway, this is the document, this is the specification, the Quarma block chipper family by Roberto Avanzi. I also hope I spell his name correctly, from Qualcomm. And it's interesting. I'd recommend, especially recommend, look at the 4 sections, security analysis of the algorithm. Okay. Consider possible attacks on this new exploit mitigation technique. First is guessing and forging PEC values. Any crypto can be cracked, of course, and it depends on the resources we need to crack the crypto. Theoretically, Quarma should be very, very strong. It's very hard to crack, theoretically. Another possible attack is pointer substitution attack. various types of pointer substitution. We can try to find already Cyanide pointer in memory and use it in evil way. And key management, due to generation keys and creating keys is up to software. If software does it bad, does it weak, we can try to attack this as well. Interpreters and just-in-time compilations, JIT, GIT. GIT is probably the best attacking vector here, and actually I think it will be the only real attacking vector for the code protected by the new instructions. Okay, what about the real world? Okay, actually I'm finishing now, and at the end, about the real world. In the real world, GCC and LVM supports the new instruction set. In the real world, the only system on chip implementing the new set of instruction is the latest Apple A12. So in the latest iPhones, you can see these instructions implemented in hardware. And theoretically, it should prevent exploitation of memory corruption vulnerabilities on the newest iPhones, but in practice, right after the new iPhones was released by Apple, the Pangu team, Chinese hacking team, tweet that they already have a proof of concept jailbreak for the newest iPhones. This means the new instruction set did not actually help. Maybe they found an attack vectors with JIT, probably. I don't know, I'm not sure. Okay, that's it. Finally, I'd like to provide some links if you wanna dig this field deeper. If you wanna dig this new instruction set deeper, start with these links. It's totally okay. And now, if you have questions, ask questions, please. If you have no questions, this is my contacts. That's it. As I promised, it was quickly and I hope more or less simple. That's it.
HackIT. Exploit blockchain.